I'm Zhang from Tsinghua University. Today, I will talk about our work on how to build a memory management system that is built for CXL-based distributed shared memory. And this is a joint work from Tsinghua, Alibaba, and Intel. In the first part of this talk, I would like to present the benefit of using CXL to build a distributed shared memory. And then we will discuss why we think that tolerating partial failures could be a major challenge in such systems. And finally, we will talk about our solutions and the corresponding evaluation results. So, CXL is one of the most popular buzzwords in recent days, and actually we are also surprised by the capability of CXL to enabling fine-grained and efficient access of the remote memory. Actually, according to our evaluations on the real hardware, we see that for CXL, if we can, the latency of accessing a remote CXL-attached memory is less than 400 nanoseconds, which is very efficient. And also, the development of CXL is very rapid, which means that the forthcoming 3.0 version of CXL promised to provide not only memory pooling, but also memory sharing, which means that the same region of remote memory region can be mapped to multiple machines, and the cache coherence of concurrent access from different machines can be automatically handled by the hardware. So it is easy to imagine that once that hardware is ready for production, we are able to build an efficient distributed shared memory on it. And in this slide, we present CXL shared memory, which is our prototype implementation. As we can see that the reference of memory spaces that is allocated from one node can be directly sent to another node. And both these two nodes can concurrently access the same address of the remote memory with the cache coherence guaranteed by the hardware. And so this is very efficient, and we just need an easy-of-use interface. In our system, we provide an interface that is just a fusion of the traditional malloc and the smart pointers, which provide a reference count-based automatic memory management. And these tools are actually already prevalently used in the current concurrent programming. We just extend their usability to a distributed environment so that you can build, with these tools, you can build a distributed application that is as easy and simultaneously as performant as a concurrent application. So as an illustration, based on our system, we build a path-by-reference RPC system, which means that, as you can see, for transferring a data, we do not need to copy the data payload from one node to another. We just need to exchange the reference, and also we avoid the network stack processing. These two merits in joint, which have led to a more than 4 times higher throughput than a traditional RDMA-based RPC system that needs to pass the value. But however, although there are many merits of using DSM, the DSM also implies an important challenge of tolerating partial failures, which means that different from full failures where all the clients will crash simultaneously, in DSM, it is possible that only some of the clients is crashed, and the remaining alive clients should still get some process. They should not be stored by these isolated crashes. And from the perspective from a memory management system, the most important challenge that we want to solve is the challenge of memory reclamation. As you can see that since some of the nodes were crashed unexpectedly, they may not be able to correctly release their memory references. So it leaves to our system to correctly and automatically identify who and when we can reclaim these memory spaces to avoid a memory leak. And simultaneously, we also do not want to incur other problems, such as a wild pointer. And to further understand and demonstrate this challenge, here we divide the procedure of reference count maintenance into 2 sub-steps, and which will help us better understand the corner failure cases. As you can see that specifically, if we want to attach a reference, we must first increment the reference count, which step in the following of this presentation, we will call it modify ref count. And secondly, we will also need to link the reference by setting the value of the reference to the address of the referenced space, which step in the later of this presentation, we will call it modify ref. And similarly, if you want to detach a reference, it involves also two steps, which is decrement the reference count and setting the value of the reference to none. Although there are only two simple steps, this basic procedure cannot handle failures, because you see that if there is a crash happen just in between these two operations, we will encounter with many problems. For example, if we increment the reference count first, but we are not able to link the reference because of a crash, we are looking at a memory leak, because this incremented reference count will never become 0 in the future. And similarly, if we link the reference first, but not able to increment the reference count, we will look at a wild point problem, because the space may be reclaimed automatically in the future. So since this is a problem of torrenting crash, an obvious rescue might be that we can use a redo-based mechanism. But if you explore this method further, you will see that the basic redo lock does not provide the rescue that we need. And the important thing here is that this modify ref count step is not idempotent, which means that it will lead to different outcome if it is executed multiple times. And the only certainty that this redo log provides us is that there is indeed a failure happen in between the recording and the clearing of redo log. But crucially, we do not know whether this crash happened before this modified ref count or after this modified ref count. So during the recovery, we are left wondering whether we can redo it or not. So this is the most important challenge that is solved by our paper, and it is solved with a two-step manner. In the first step, we try to use lock to make this step idempotent, because that if we lock the referenced object, we make sure that no other client can concurrently modify this reference count, which enable us to record this modified value into the redo log. And we can use that information during the recovery, which essentially make it an idempotent step, which is much more recovery friendly. But however, this lock-based mechanism is only suitable for 4 failure scenarios, where all the clients will crash simultaneously. And the problem here is that if you use lock, you introduce the blocking problem. And just imagine that if you have a client that is crashed after requiring a lock, until the recovery of this client, all the other clients that intend to attach or detach a reference to this object will be stored by this crashed client. And this will cause the so-called cascading blocking problem, which should be tolerated in our model because we want to tolerate partial failures. So, navigating all these challenges, a final question emerges, which is how can we craft a non-blocking algorithm that help us to correctly maintain the reference count. And we can see that this is actually possible because all the other steps except this modified ref count step are idempotent by nature. So this observation leads us to execute this step first and use its successful execution as the commit point of the whole procedure, which means that this step will never be re-executed during the recovery. But if we identify that this step is executed before the crash, we can blindly redo all the following steps during the recovery because they are idempotent by nature, and it doesn't matter whether they have already been executed before the crash. So this is the key idea. And based on this framework, we found that our task transformed, and the final task is how can we identify whether this single step, this modified ref count step, has been executed before the crash. And this task is solved by packing more error informations with the reference count, and we manipulate all these fields with atomicity. Specifically, as we can see from this figure, we actually pack 2 more fields with the reference count in the same cache line, which include the client ID of the last client that has successfully executed the modify ref count step on this object. And also we include the error of that last successful transaction. So we have 3 fields here, and we manipulate them with a single compile and swap instruction to guarantee the atomicity. And with these additional information, we somehow maintain a global distributed timeline. We throw a M multiply M error matrix, where M is the maximum number of clients. As you can see in this figure, that for every client I, it will maintain the error II, which is incremented by 1 for every execution of the reference maintenance function. And this client I will also need to maintain all the columns in the same row of the matrix, where every error ij actually represents the largest local error of client j that has been observed by client I. So essentially, this is just a distributed vector clock that just uses the interaction on this distributed reference count as distributed messaging events. So with the help of this distributed vector clock, actually, we can decide whether this modify ref count step has successfully executed by comparing the local error timestamp that is recorded in the redo log with the current global error matrix. And this is the basic procedure of our algorithm. But actually, the provement of the correctness of this algorithm is very complex and involve many corner cases to be discussed. So I will skip the detail here, and if you are interested, you can refer to our paper. Okay, so with these technicals, actually we built the CXL shared memory system, and we also tested it on a real CXL hardware. And as you can see, that this is our test platform. We have 2 separate computation nodes, and they are both directly connected to a shared backend memory node, which is CXL attached. And importantly, all these 3 devices have independent power supply. So we can see that they have separate failure domains, and we need to handle and tolerate the partial failure problems. And at first, we first evaluate the memory allocation throughput of CXL shared memory, because basically it is just a memory allocator. And as you can see that here, CXL shared memory can deliver more than 50 million allocations per second, which is more than capable for the usage of many distributed applications. And we also compare it with Relloc, which is a state-of-the-art NVM allocator. And we can see that the performance of CXL shared memory is much more than Relloc. And also, Relloc does not support the sharing of allocated memory spaces. And the Relloc can only tolerate 4 failures, cannot tolerate the partial failures. So these are all the benefits of CXL shared memory. But however, we also found that the performance of CXL shared memory is still 2 to 5 times slower than mymalloc or jemalloc on local memory. Because that we think this is acceptable, because that the latency of CXL memory is still higher than local memory. And also, there are necessary costs to tolerating failures and to support the sharing of the allocated memory. So, to further understand this cost, actually we present a breakdown analysis for this work. And you can see that there are 2 main sources of the overhead for our system, which include the additional allocation for the reference count, which is used in the automatic memory management. And also we incur an additional flush instruction to flush the data to the CXL memory, which each will count to about half of the overhead. But since that we only add one additional flush as instruction for every allocation, we think that this overhead is necessary if we cannot amortize this overhead with some maybe a batching solution. So this is the performance of the basic memory management. And we also build a distributed key value store that is on top of the CXL shared memory. And we compare it with Intel TBB's concurrent hash map and the Lightning. Well, Lightning is a state-of-the-art single machine, but multi-process key value store that is also based on shared memory. And as you can see in this figure, the performance of CXL shared memory is much higher than Lightning because Lightning is still based on lock, and we just use non-blocking algorithm. And more importantly, the performance of CXL shared memory is on par with the performance of TBB's concurrent hash map, which is a single machine application. So we think that this is a great demonstration of the capability of CXL shared memory. It allows you to develop distributed application that as easy and simultaneously as performant as a concurrent application. So that is the overall information of our work. And as a conclusion, actually, we think that currently it's a good time to revisit the distributed shared memory model in this CXL era. And we also think that non-blocking algorithm will play an important role in the future research on the CXL because that it can help us to tolerate partial failures. And the source code of our system is also open sourced. You can use it and contact us if you are interested. So that's all of our presentation. Thank you, and I'm ready for the questions.
Right? Questions? Yeah.
Hi, Matthias Hille, Barkhausen Institute. Great talk. Since you look at distributed shared memory, if I understand correctly, you use the shared memory to implement your logs. Is that right?
The distributed shared memory is just a unified memory address to host the shared data. But we do not use log because it is blocking. Okay.
But you had some sort of a RPC between the nodes. How do you implement that?
Oh, okay, sure. So this is our implementation of an RPC system. So as you can see that we just allocate the payload on the distributed shared memory, and we exchange the reference to this payload. So we do not move the data, we just exchange the reference, which is much lightweight.
And do you have any intuition how this is influenced if you exchange the reference via an actual message passing operation?
I see. Actually, this details is included in the paper. We have implemented a ring buffer on this shared memory, and we use that ring buffer as the channel for these messages.
All right, thanks.
Thank you.
Hi, Sam No, Virginia Tech. So your target problem is about partial failures, right?
Yes.
So do you possibly have any initial evidence of the failure rate or anything in that regard?
So the ratio for the possibility of a failure,
yeah,
right?
So you have a prototype that you're working with, and if you have
I see. Actually, I think that the current ratio of possibility of failure is not will not be the real failure possibility because the current test board is only a POC test board. But we think that if we extend the size of this CXL, we have multiple backend node and multiple front-end node. Eventually, we should tolerate partial failures. This is, in principle, it is a necessary task that we should tolerate. But the current failure possibility is very high, but we actually do not know whether it will be real because it is just a POC test board.
All right, thank you.
Okay.
Hi, Kevin Laughlin, University of Michigan and Google. Thanks for the great talk. I had a quick question about the ref count mechanism. So does this first off mean that traditionally read-only operations now become read-modify-write to modify the ref count?
If you share the data with different machines, for example, here, as you can see that we have two reference to this object on different machines, so the ref count is 2. So the ref count is just for automatic memory management.
Yes, but I guess what my question was is that at the memory controller level, the writes will interfere with the reads that other people are doing because the bus has to turn around to process the writes. So I was wondering if you've investigated or looked into at all what the specific performance penalty is potentially from the extra writes being on the memory bus.
Yeah, I see. So actually, because of the additional compare the swap instruction, so this there will be necessary cost for this reference count mechanism. And actually, in our paper, we have used some micro benchmark to test the performance of CXL. The CS instruction will be much heavier than read and write, but we think that this is necessary because otherwise we cannot design this automatic memory management.
Yeah, got it. Thank you.
Thank you.
Phil.
Phil Levis, Stanford and Google. First of all, thank you. This is great work. I think actually if you move away from the Intel FPGA is soft IP, so I think once you get hardware IP, it's going to be even, you're going to get much better results, and so that's even encouraging. I'm wondering if you can go to slide 28, because I have a question about the results on slide 28.
You mean the result on?
Yeah, slide number 28.
28, okay,
Yeah.
sorry.
Yeah, so when we see those curves flattening on the left on the thread test, is that because of bandwidth? Because I don't have a sense as to what the read-write sizes are. Is that because of bandwidth over the CXL bus, or is that because of, issue queues within the memory controller? Do you have any idea what the source of that bottleneck is?
Actually, we currently have not do such a detailed micro benchmark, but according to our analysis, it is bounded by the maximum IOPS of the flash instruction.
Great, thank you.
Thank you.
So another real quick question, since we have only 3 papers.
Okay, thank you. Zhang from Shanghai Jiang University. I have a really quick question about, I'm curious about the overhead of the logging. So you have mentioned that you use redo log.
Yes.
Is the logging overhead, the flash overhead in this figure, or?
I see. Actually, so this is not very correct here. We include that additional logging and additional reference count in this alloc. So because we think that they are additional allocation in something like that. And as you can see that half, the flash is consists of half of the overhead, and the others consist the other half.
Okay, I can understand. Thank you.
Thank you very
Let's
much.
thank our speaker again.